Alright, so two things today, right? Analyzing polynomial functions and transformations of polynomial functions. John, did you find one? Doesn't matter? Huh? Okay. You can always print them off. They're in school, you just print off the notes. Okay, so for g of x is 2x to the fifth plus x to the fourth minus 30x cubed plus 64x squared minus 52x plus 15. What? The degree of the function is. So what degree function is this? The degree 5. Sign of the leading coefficient is? Are you sure? I'm positive. The function extends blank in quadrant blank and blank. So what is it? Let's go. Yeah, okay, and extends up in quadrant 1, okay, and down in quadrant 3. I always like to go kind of left to right. So say what's happening in either quadrant 2 or 3, and then what's happening in either quadrant 1 or 4. The y-intercept is 15. The potential integral zeros are 1, 3. So the potential integral zeros are the integral factors of 15, right, of the constant term. The equation of the function in completely factored form is, okay, so we have some work to do. So we could graph this. And if we graphed this, come on. I had this pre-graphed, right? Because it's not like it's an easy thing to graph. There we go. So if we graph this, and this is just a standard window, right? So we're not seeing the 15 y-intercept, but we could see that 1, 2, 3, 4, 5 looks like negative 5, right? Okay. So if it's negative 5, what am I going to divide by? Divide by x plus 5. Okay, and what's the function? So we've got a 2, 1, negative 30, 64, negative 52, 15. And if this is in fact a factor, then what are we going to see here? 0. Okay. So, go ahead.
Is that 64?
It's 64. So do your synthetic division. Might as well get some synthetic practice division-ish stuff in. Okay. So negative 5 was a 0 and gives us this. So what degree is this now? So this is degree 5. This will be 1 less. So now we have a degree 4. Then we got to keep doing the same thing, right? Until we can get it down to a quadratic, which is something that we can factor. So we have to factor. So we need to try something else. So we go back here. Say something's happening at 1, it looks like. Okay. I'm not entirely sure, but that's a potential 0, right? So let's try it with, if that's 1, what am I dividing by?
X minus 1.
X minus 1. Okay. So here, maybe just make a note. We're going to try x equals negative 5. We're going to try x equals 1. Okay, and I got the numbers, 2, negative 9, 15, negative 11, 3. And we just, do the, what's that? Yeah, okay, nice. So that worked. Okay. I mean, go through it, make sure you give it a try. You should just be looking up here and saying yes or no.
Why are you dividing by the new polynomial?
Well, we've got a quartic, but we want the factored form of this thing. It's of degree 5, right? So it could have 5 different roots.
Oh.
Okay, so we found one, right? So we said, looks like -5 is the root. Tried it, yeah, okay. Divided by the factor, x plus 5, yes, that worked. Remainder was 0. Okay, remember, factor theorem says if the remainder is 0, then that's a factor. Looked at the graph again. And said something's happening at 1. I'm not actually 100% sure what's going on here. I do know it has to go up here, so yeah, we could take a closer look. Well, or we can't take a closer look. Okay, so I'm going to try a zoom box. Or not. I don't know what I'm doing here. It's the calculator, it's off with the screen, right? So, hang on. Let's see if I can do this here. Okay. I'm going to have to hit down about here. Yeah, this is not going to very nicely, easily. You know, so let's default to Desmos and just type this in. 2x. So keep in mind, obviously you have to use your calculator. And I was honestly trying to. So 30x cubed, 64x squared, minus 52x, plus 15. Okay, so look what's happening here, right? It looks sort of cubic, almost, right? And maybe if we can zoom in, how do we zoom in? I think actually I could do it on here, maybe. So if we zoom in, okay, so if we zoom in, we can see out here that was our -5. This looks cubic, so, and then we've got something here at, what is that, like 1.5? Okay, all right, so keeping that in mind, if we just did x minus 1, let's do x minus 1 again, right? Because 1 will be a factor how many times? Looks like at least 3 times. Well, it has to be exactly 3, right? It's not 1. It's 5th degree, and we've already got 1 root there. So and then there's one obvious one at like 1.5. Looks like 1.5. Okay. So just try x equals 1 again. So what degree is this here? We've got constant. This is cubed, right? So 2. Okay, 2, -2, -5, 5, 3, -3, 0. Okay, so that worked. So what have we got so far? We got factors of x plus 5, x minus 1, and x minus 1. So we could say, okay, so g of x is equal to x plus 5, x minus 1, x minus 1, and then this, which is 2x squared minus 5x plus 3. Now, that probably factors, right? Actually, we know it factors because we saw the other roots. So g of x equals x plus 5, x minus 1, x minus 1, 2x, and then x. And it's going to be minus 1 minus, so that's 2x squared minus 2 minus 3 is minus 5 plus 3. So there we go. I faked, actually knew it was that, right? Because I knew the roots. Yeah, there was a root of 3/2. So 2x minus 3 is a factor. So then writing this out, we should collect the x minus 1s. So g of x in factored form is x minus 1 quantity cubed, and then an x plus 5, and then a 2x minus 3. Okay, so that all started from, we have this equation. It's of degree 5, the leading coefficient is positive. Here's my potential integral zeros. To get the factored form, I need to see which of them are 0, so I can graph it, pull out a 0, divide, right? Well, change the 0, right? This is 0 into the factor, divide by the factor, make sure it is, right, that I have a 0 remainder. Do it again with another factor, do it again with another factor, get down to a quadratic, which is then factorable, and answer the question. Okay, so questions on this first bit? The zeros and their corresponding multiplicities. Okay, so we have a factor of x minus 1 cubed, which gives us a 0 of x equals 1 with multiplicity of what? Multiplicity of, pick a number, any number, as long as it's 3. Yeah, multiplicity of 3, right? It's x minus 1 cubed. So it's good. For a short day, this has been a long day. What's another one? X equals negative 5 with a multiplicity of? Of 1. And the last one? X equals, so you've got 2x minus 3. 3 halves. 2x equals 3, x equals 3 halves, so x equals 3 halves with the multiplicity of 1. Okay. Now remember, the test for this is coming up Monday, right? You got Friday off. There is a quiz online. You should be getting into that soon. We will finish tomorrow, right? So tomorrow or Thursday? Wait.
Tomorrow's Wednesday.
Tomorrow's Wednesday, yeah. And then, so tomorrow I think we finish the unit off. Thursday we start the next section. Friday is not a day here. And then Monday is the test. Okay, sketch a graph with all the intercepts labeled. Well, okay, we kind of already know what this looks like. So we have a y-intercept of 15. We have an x-intercept of negative 5. On my count. Okay, and we already graphed it, right? But what do? We know it goes from Q3, right? Down in Q3, so it's here. Comes up, comes back down with a multiplicity of 3 here, and then goes through 3 halves. Right there. Okay, arrows on both ends, that's the shape, right? So indicate this here, right? Multiplicity of 3. And we want to know the intervals. Who's that? We want to know the intervals where g of x is positive. So where is it positive? Negative 5 to 1. Okay, negative 5 is less than or equal to x is less than or equal to 1. No objections to that? Yeah, what's the object? Just strictly less than, right? Yeah, what is it at negative 5 and 1? It's equal to what? It's equal to 0. Okay? So when we're doing intervals of positive and negative, right? And then remember on the test, just be consistent. There's nothing here to tell you couldn't have used interval notation, right? But on a test, if we give you something in set notation and you give an answer, it should be in set notation. If we give something in interval notation, it should be, and if it's open, then it's open. This one's open. You could do set notation, you could do interval. Okay, where else is it positive? It's like, give up already. Okay, so from negative, yep.
Because what is equal to it?
What is equal to it's 0, and that's not positive. And then in sympathy we get, where is it negative? So if it's less than -5, it's negative. Where else? Between and okay, between 1 and 3/2, right? So 1 less than x less than 3/2. So negative anywhere below -5. Between -5 and 1, it's positive. Between 1 and 1.5, it's negative, and greater than 1.5, it's positive. A certain regularity. It's like listening to the bell and hearing a log bell. Yep.
So for the calculation, right? Reduce by x minus 1.
Okay, hang on. So
instead of adding it to a quadratic,
so you're gonna have to do 3 synthetic divisions. Go with 4th degree, 3rd degree, 2nd degree. You go from easy to quadratic.
Yeah.
You could.
You turn it off.
But quadratic, we should be decently able to factor. Okay. So the question was, if we could just use the roots to take it down to degree 1, instead of factoring the quadratic, to then just divide by another x minus 1 and end up with the remainder being linear, right? So we have x, 2x minus 3. We just get the 2, the 3, and the 0. And yes, you can. Okay, but once you're down to a quadratic, it's generally pretty easy to factor. So either one will work. Okay. I mean, the problem's going to come if the quadratic doesn't factor and we have to find roots. We have to use the quadratic formula, right? So at that point, it doesn't factor, so you can't, you know. The width and height of a box are represented by x and 5 minus x, respectively. If the length of the box is 3 times the width, then state the restrictions on x. So what should we do? Let's draw a picture. I got a box. The width is. It was just a tentative. Not drawn to scale. So let's call that the width. So the width is x. The height is 5 minus x. That's here. And the length is 3x. Okay. State the restrictions on x. So what do we know about x? Or what do we know about 5 minus x? It's going to have to be bigger than 0. It's got to be greater than 0, right? We can't have a... So if we start to say, all right, look, 5 minus x is greater than 0, so negative x is greater than -5, or x is less than 5. So the restriction on x, it's between 0 and 5, right? So restriction on x, it's going to be between 0 and 5. So 0, less than x, less than 5. It can't be 0 and it can't be 5, right? If it were 0, then the volume would be 0. There wouldn't be a box. And if it were 5, again, there wouldn't be a box because it would have no height. Graphically determine the maximum volume of the box to the nearest tenth of a cubic centimeter. Okay.
We have another step on ours.
Do you? Oh, okay. What do we got here? Wow, that's it. So state the formula. Okay, so what's the formula for the area of this box, volume? Formula for volume. Okay, so what's V equal to? Yeah, so x times 3x times 5 minus x, which we can expand out. Right, so what's that going to be? Well, okay, how far do we need? We don't really need to expand it out. Let's just do this. The volume is 3x squared times 5 minus x. Okay. And if we're going to graph that, okay, now does it say graphically determine?
Yeah.
Graphically determine the maximum volume of to the cubic centimeter. So what kind of a window are we going to set for this? Actually, I think I'm going to kill this and reopen it because it was off by a little. Okay, so what window are we going to use for the x's? So let's say 0. We could go 0 to 5, right? Because we know it has to be between 0 and 5. You could also go maybe 0 to 6, just to give yourself a little room on the one side, by ones. And what's the volume going to be? Well, so we just, take a guess. I don't know. How big could the volume be here? So we know it can't be below 0. So how high are we going to go here? Well, yeah, okay. What if this were 5 and this, we just ignore that, and 5 squared would say 75, so maybe go up to 100. Just as a, and you can refine that, right? So let's go 0 to 100 by tens. And what we want is y equals 3x squared, bracket, 5 minus x, bracket, and we'll hit graph. Let's just see what we see. Okay. Okay. Good enough. So that's part of the cubic, right? Part of the cubic. There's part that probably does this. Right? Well, we know it comes from down there and then it's going to turn around somewhere else. But this is what we're interested, and that's the maximum that we're interested. So second calc max, that's pretty close. We'll move over, so left bound, right bound, take a guess. Max, x is 3.3333333. And what is what? Graph turn the maximum volume. So the volume is, what is it, to the nearest what? 100, so 55.56. Tenth, 55.6. So the volume is 55.6 cubic centimeters. Okay, and we could say when the width. It's 3.3 repeating centimeters. Okay, didn't ask for the width, just asked for the volume. If I go back here and just do a standard zoom and just sort of say, so what does this look like as a cubic? Okay, so we can see it's doing this little bit here, right? So it's got a negative, right? If we multiply that out, we'll get a negative 3x squared, so it's up in Q3. Q2, it's up in Q2 and down in Q4 because of the negative leading. We're only really interested in this part of the in this part, he says, circling the whole thing. We're really only interested in this bit in here, right? Like what's going on in there. This does that. That would be a negative volume, and any volume over here would be based on a negative width or negative. So that doesn't make any sense. All right, thus finisheth the first part. Transformations of polynomial functions. All right, it's the same transformations you've already done. Everything is exactly the same. If I want to do a vertical stretch by a factor of 4, I will replace the y with a 1/4 y. If I want to move left 3 units, I will replace every x with an x plus 3, and so on. Right? Nothing has changed. Okay, which is why you'll look back later at transformations and go, wait, this was so easy, right? Because we're just getting more into it, right? We're going to do them again, and again, and again. And now we're doing them with polynomial functions, and just remember, nothing's changed. Describe the transformations in the correct order that were made to the graph of y equals x cubed. So this is what we ended up with. So what we might want to do is do a little rewriting and get it into a transformation form that we're used to looking at, right? So we might say y minus 3 is equal to negative 1/2 x plus 4 cubed. And then get rid of that negative 1/2, bring it over here where it becomes negative 2 times y minus 3 is equal to x plus 4 cubed. And so now we can look at that and we can list our transformations in order, in the correct order. So what's the first transformation we look for? Stretches. Okay, are there any stretches? Okay, what kind of a stretch? So Vs by a factor of 1/2. Okay, you're all certified stretch experts now. We no longer need to say about the x-axis. We should always remember that that's the case, but okay. Any other stretches? Is there a horizontal stretch? No. Okay. Are there any reflections? Okay, where? So reflection about the x-axis. Any other reflections? No. Translations? So horizontal translation. Which one? Somebody said right. Left 4 and a vertical translation. Up 3. Okay. There we go. Those are the transformations, right? That's what happened. So if I have to draw this, or if I have to map a point, I got the words there, right? I just got to do what it says. The point negative 464 lies on the graph. Determine its corresponding image point. Okay? So we have negative 4, negative 64. I'm going to undergo transformation number 1. This just refers back to what's above, right? So under the first one, so vertical stretch by a factor of 1/2, where are we now? So negative 4, negative 32. Undergoing transformation number 2, this becomes the point. Negative 4, positive 32. And undergoing 3 and 4, because we can do them both at the same time. If I go left 4, where am I? Negative 8. And I go up 3, 35. So the point negative 464 will map to the point negative 835 after undergoing these transformations. So where does xy go to? Now we could do this in 4 steps, or we can just kind of put it together. If you want to check, once you've got this entered here, stick in the negative 4 for x and make sure it ends up as a negative 8. It doesn't mean you did it correctly, but at least it means it's not wrong necessarily. And do the same thing. So okay, what happened? There was a vertical stretch by a factor of 2, right? So we're going to get a 2y. It was reflected, so it's going to become a negative 2y. It was moved up 3, so it's negative 2y plus 3. And this went left 4, so it's x minus 4 and negative 2y plus 3.
Was it 1/2?
Oh, right, it's a half. Sorry. It's good, see? But see, I told you knew transformations. Negative 1/2 y plus 3. Okay, if I put the negative 4 in there, negative 4 minus 4 is negative 8. It matches. Doesn't mean it's right. Maybe it was a stretch by a factor of 2 or something, and it should have been a 2x, but you do get negative 8. Put the negative 64 in there. Negative 1/2 times negative 64 is positive 32, plus 3 is positive 35. It's consistent with what's written there. The graph y equals x cubed is shown on the same graph. Accurately sketch the graph of y1, blah, blah, blah. All right, let's start with our favorite point, 0, 0, right? It gets stretched, so what? It gets reflected, so what? And then what? It moves left 4, up 3, right? The only thing that moves this point, 0, 0, is the translation. So left 4, up 3. I'm going to pick 2 points. This is one of the points, right? Because it has an even, right? It's a point 28, so it's even. So vertically stretched by a half, it's at 4. Reflected, it's at negative 4. And then go left 4. 1, 2, 3, 4. 1, 2, 3. So that's there. And let's do the same thing with this guy. Right? It's an even number, right? So that from -8, vertically stretched by 1/2, reflect, left 4, we're going to end up off the grid, so let's go up 3, and then 1, 2, we're out here somewhere. That's just the fault of the people that made the worksheet. And this is this, right? That's it's called a point of inflection. It's the change in concavity, the change in direction. So there's a change in direction happening here, which means it's going to come down here, flatten out, change direction, and go down like that. And it's kind of a bad grid. It would have been better if we reflected on the y-axis as well or something. Well, even then, it would have just ended up off the other side. It's not great. We'll try and avoid doing that on a test, right? Because then it's off grid, and then you think you're wrong when you're right, and that's bad. All right, number 2. How much time do we have? Oh, tons of time. Take 15 minutes. Work your way through number 2. Okay, and we'll go. All right, so you have had a chance to look at this and try something out, right? And maybe you're on the right track or maybe not, but let's go through this and just see, so how do we handle this particular type of question? So what's the y-intercept of the original function? So basically you're putting in zeros for the x's, and it becomes -4 times 1 times 2, or -8. What is the y-intercept of 1/2 y? Okay, what's 1/2 y doing? Vertical stretch by a factor of 2, so then this becomes -16, right? Okay, so you can just make a note in here if you want, vs by 2. What's the y-intercept of 1/4 y? So what's this? It's a vs by 4. Oh, it's over here. So it's a vs by 1/4. So we have to watch that, right? If it's over here, you just read it as it is, or move it back over where it becomes 4y equals. Okay, so then -8. Remember, we're not talking about this guy. We're talking about this. So -8 would then be what? -2. Okay, and then you used your graphing calculator to verify that. What are the zeros or the x-intercepts of the polynomial function? So the original function. What were they? 4. Okay, so I have x-intercepts of 4, -1, and -2. What are the zeros of y equals p of 1/2 x? So what's happening here? So I got an hs by 2. Okay, so where's the 4 now? Horizontally stretched by 2. Moves to 8. Where's the -1? Where's the -2? So those are my new intercepts, right? Because they're on the x-axis, that's not the line of stretch, right? But they're twice as far away from the y-axis as they were before. Write the equation of y equals p 1/2 x. So now I know, well, here are my zeros, right? So what are the zeros? We've got x minus 8, x plus 2, x plus 4. Okay, and then we should say, I suppose, y equals. But wait a sec, we have a 1/2 x, right? So we can't really write it like this because now we're changing things we shouldn't be changing. So we need to go back and rethink this and say, well, everybody's seen x, I'm going to write 1/2 x, right? It's p of 1/2 x. That says wherever you see x in the original, you write 1/2 x. So it's a 1/2 x minus 4, a 1/2 x minus 1, or plus 1, and a 1/2 x plus 2. But wait a sec, I mean, my intercepts are supposed to be the 8, the -4. You know, how are you getting an x-intercept of 8 here? Well, think about it, I got 1/2 x minus 4 equals 0. So let's rewrite this, right? We can take out these halves to get it in this form, because I don't want a 1/2 x, right? I just want an x. So I take this half out, so it becomes 1/2 of x minus 8. That's this guy. This guy becomes 1/2 of x plus 2. This guy becomes 1/2 of x plus 4. And see, now we've got the intercepts where we want them, right? There's your 8. There's your -2. There's your -4. We're going to collect the halves together in front, right? So it's y equals. So it's y equals 1/8 x minus 8 x plus 2 x plus 4. Right? So the idea is just go into the original, everywhere you see an x, write a 1/2 x. Okay? But we don't want that, right? So we're going to factor out the halves. When we do that, we basically just double everything, right? That doubles becomes an x. That doubles becomes -8. This now matches up, or this at least, matches up with this, right? We now have, oh, yeah, there are my intercepts, right? Right where I said they would be. Okay, next page. Nope. Keep going. What are the zeros of the transform function if p of x was horizontally stretched by a factor of 1/2, then reflected over the y-axis? Okay, so what was it? So this is 4. So stretched by a half, where's it going to go? 2, then reflected over the y-axis? -2.
That's not the transform function. That's the original.
Yeah, so horizontally stretched. So p of x, this is p of x.
That's the original.
Yeah, that's what I want. Because
It says for the transformed.
it says, what are the zeros if p of x, the original,
It says of
What are
The
the
transform
zeros of the
function.
transform?
what are the zeros of the transform function if p of x, the original function, was horizontally stretched by a factor of a half? It's a new transformation. It's a different. It's not of this transformation.
But you told me it was the
I lied. I wouldn't trust me. I can't even throw myself that far. Sorry, if I told you that, I was wrong. So, -1, half of that is -1/2, reflected over the y-axis will be +1/2. Okay, so +1/2, and the other one was -2. Half of that is -1, reflected is +1. Write the equation of the transform function in terms of p of x. Okay, so how do I do? So I'm going to write what? Well, I'm not going to write anything. There's a big number 9. Okay, so if I want to do a horizontal stretch by a factor of a half, what gets replaced with what?
2x.
X gets replaced by 2x. If I then want to reflect over the y-axis, then the x will be replaced by a -x. So we end up with p of -2x. Okay. Now, following form, in terms of x then, what I'm going to do is everywhere we see an x in the original, we're going to replace it with -2x. So in terms of x, it's going to be y equals, okay, so what did we have? Originally it was x minus 4, what was the original? Yeah, it'd be like, yeah, x minus 4. So that's going to become -2x minus 4. And it was x plus 1. So -2x plus 1, and it was x plus 2, so -2x plus 2. So we're just going back to the original function, right? The original function was p of x is x plus 4 times x minus 4 times x plus 1 times x plus 2. And p of -2x says, wherever you see an x, write -2x. Write it in the form. So now we say, okay, I got all these -2's in here, right? I want it to be x plus b, so I need to factor a -2 out of each set of brackets. Okay, so factoring a -2 out of each set of brackets will give us, where can I write this? Let's try here. So y equals -2, and then we get x, what? Yeah, plus 2, right? So I need this times this to be -4, right? So basically I'm just dividing by -2. And then we've got a -2, and I've got x. You're right. Good call. negative 2, and then we've got x minus 1/2, right, because that's we're going to do the plus 1. And then we've got a negative 2, and we've got x minus 1. Okay, so I'm going to pull all the negative 2's together. So y equals negative 8, and then I get x plus 2, x minus 1/2. That's a bit non-standard, but they wanted it in this form. They wanted just an x, right? This should be written as 2x minus 1, but we're not doing that because they said, hey, write it with an x. Okay. And from this, actually, we can read then, what are the zeros? Negative 2, positive 1/2, positive 1, right? So this goes back to where we said, what are the zeros? And we just took the positive 4 and did stuff to it and turned it into a negative 2, and this balances that off. Josh? Which way does it go? If P of X were transformed, do you have just one challenge? You don't have the H. You have two, G and H? Okay. I don't see H on here. Okay, if P of X were transformed, so his new equation was y equals 2x minus 8, 2x plus 2, 2x plus 4, describe the transformations that took place. Wow. Okay. So, how are we going to look at this one? Well, let's start off by factoring out. So 2, and then we got x minus 4. Okay, let's throw the 2 in brackets. And a 2, and then we got x plus 1. And a 2, and then we've got x plus 2. Okay, so we factor out all of these guys, right? So that becomes an 8. So y equals 8, x minus 4, x plus 1, x plus 2. The transformation is, what is that? I mean, we could just say x minus 4, x plus 1, x plus 2. That's P of x, right? So we could write y is equal to 8 P of x. Or you could write 1/8 y is equal to P of x. And from either of these, vertical stretch by a factor of 8, or it's a vertical stretch by a factor of 8. So there was a vertical stretch by a factor of 8. By a factor of 8. Okay? And if you like, you can throw in about the x-axis. Okay, so you had one more, right? H? Which is not on this page. Not on this page. Okay, doesn't exist, I've got to write it out. Okay, so H. Okay, so, ready? Let's finish this off. What did you, ladies and gentlemen, test is on Monday. You're going to get questions like this on the test. I will guarantee you that 110%. Guarantee you nobody will get 110% also, because I don't think there's any bonus, right? This stuff's going to be on there. I really would feel uncomfortable if I were you sitting there Monday writing the test and realizing, oh yeah, that's that question that I just kind of sat and talked through, so I don't know what to do. So, what do we do? So we start with the original. What were the original x-intercepts? So original x-intercepts were what? 4, -1, and -2, right? What are these x-intercepts? So new x-intercepts. 12, -3. How do these compare? They're 3 times. So there must have been a horizontal stretch by a factor of 3, right? Because our new intercepts are 3 times. It wasn't a move. We didn't translate it. Translating it, you can't get, we still retained it had to be stretched by a factor of 3. So we're going to say, hey, this to this means, therefore, a horizontal stretch by a factor of 3. So what are we going to work out then? Well, we're going to say that means we need P of 1/3 x. Horizontal stretch by a factor of 3. X is replaced by 1/3 x. What's that equal to? Again, we go into the original. It was x minus 4. Now it's 1/3 x minus 4. So 1/3 x minus 4. It was x plus 1. It's 1/3 x plus 1. And it was x plus 2. It's 1/3 x plus 2. So having figured out that the original x-intercepts and the new x-intercepts are related by a horizontal stretch by a factor of 3, knowing that that means that everywhere we see an x, we're going to replace it with a 1/3 x, we simply go into the function and do that. Now we say, okay, we're going to factor out the thirds. So this is 1/3, and this will be x minus 12. Factoring out the third means multiplying everything by 3. Factor out the third, multiply everything by 3. Factor out the third, multiply everything by 3. So we're sitting here, so that's 1/27th. X minus 12, x plus 3, x plus 6. This matches with this, right? The equation we now have has the correct x-intercept, right? Has an x-intercept of 12, negative 3, and negative 26. But what have we got here? If we just went to the intercepts first, y equals x minus 12, x plus 3, and x plus 2, we would have to multiply by 27, right? So to get this back, we're going to go multiplying through by 27 to get rid of this, and go y is equal to 27 times p of 1/3 x, and then read that as the vertical stretch of 27, or rewrite this to be 1/27th y is equal to p of 1/3 x. Okay, and now from that, we have the transformed form, right? So we can now say, here's what's going on. So there's a vertical stretch by a factor of 27, and there's a horizontal stretch by a factor of 3. And if you want to compare that, you can look at your y-intercept. So back 100 pages ago, what was the original y-intercept? It was negative 8, right? What's this y-intercept here? So it's negative 12, negative 36, negative 216. Okay, so we need to get it back. Or sorry, it's stretched out. So it's stretched out. Right? So that's what's happening here. These guys were moved. It was a horizontal stretch, but there was at the same time a vertical stretch by a factor of 27.